Hello, my name is Joseph Ho. I'll be presenting a talk titled Experimental Quantum Conference Key Agreement using a Photonic Graph State. This experiment was conducted at Heriot-Watt University in Edinburgh alongside my colleagues listed here, including theory support that was provided by Federico, who's based in Heinrich University in Dusseldorf. In this talk, I will introduce what conference key agreement is and briefly summarize our previous work in this area. I will then introduce our new work using a photonic graph state for investigating two approaches to conference key agreement in a network setting. This includes how we prepare the six-photon graph that is used to distill different resources, namely GHZ states and bell pairs, which can be used in the different approaches to implement conference key agreement. I will then summarize the results of our work. So quantum conference key agreement is a cryptographic primitive that allows end users to share a common secret key. Broadly speaking, this can be achieved in two ways. The first is to use traditional two-user quantum key distribution to establish keys in pairwise fashion among the group of end users, followed by a step of transformations on the key pairs into a conference key. To see this, let's consider the standard two-user setting. We have Alice on the left, Bob on the right, and they perform QKD using their devices such that they end up with identical secret keys on each side. We note here that a key here just refers to a string of randomized bit values. Moving to the conference key setting, we have three users, Alice, Bob, and Charlie. As before, Alice and Bob can share a pairwise key using QKD. Then Alice and Charlie separately does the same and obtains a second key pair. Note that each of these pairwise keys are unique, and as such, in order to use this in a conference key agreement setting, Alice will need to coordinate with one of these users to transform these keys such that all three users end up with a common key at the end. We will refer to such methods of conference key agreement as 2QKD. Another way of doing this is, of arriving at the conference key is to use genuine multi-party entanglement shared among the group such that the key can be obtained directly using a suitable n-party protocol where security can be proven. We will refer to these type of methods as NQKD. For a more comprehensive look at conference key agreement, including a review of recent NQKD proposals, I would suggest this review paper that was published just last year. Let's now see how one of the recent NQKD proposals works in practice. Here we have a group of four users, Alice, Bob1, Bob2, and Bob3, who wish to establish a conference key. They are connected to a quantum server that distributes multi-party entanglement. So then the question is, how do we use these states to produce a secure conference key? For this, we shall take a look at the NBB84 protocol, which has been taken from these two papers that were first proposed and proved security for generating a conference key. The protocol here consists of four main steps summarized here. The first step of the protocol is to distribute maximally entangled M-partite GHZ states to the end users trying to produce this conference key. This happens for a number of rounds depending on the length of the key to be created. Next, in each of these rounds, the end users measure their qubit according to a pre-shared sequence of measurement types. In this protocol, there are two measurement types. Type 1 measurements correspond to all users measuring in the Z basis, while type 2 rounds corresponds to all users measuring in the X basis. For an ideal GHZ state, when all users measure in the Z basis, they will obtain perfectly correlated outcomes, which allows these to be used as part of the key generation portion of the protocol. Meanwhile, the type 2 rounds will obtain outcomes which obey a specific set of correlations for the target GHZ state, and therefore can be used for parameter estimation in order to test for any added noise by an eavesdropper. We note that as a result, the type 2 rounds will occur less frequently, allowing most of the rounds to go to key generation. Lastly, in order to ensure that only the end users know what the pre-shared measurement sequence is, a small amount of key is used initially with the goal of using this protocol to generate much more key than is used. We remark that this is very much like most QKD protocols where a small amount of key is typically assumed to be used for the initial authentication purposes. Once all measurements are complete, the end users proceed to estimating their security parameters. To do this, the group discloses a subset of their outcomes from type 1 rounds, along with all the outcomes from their type 2 rounds. From these outcomes, the group can then estimate two parameters, the QBER or quantum bit error rate and QX, sometimes known as the phase error rate. We note that QBER here is defined as the largest pairwise error that is observed between Alice and each Bob, while QX here is a measure of how much deviation we observe in the correlations from the ideal GHZ state. Finally, once the security parameters are determined, the end users are left with the raw key after discarding all the rounds where they've announced previously. The end users can then apply error correction and privacy amplification on the raw key in order to produce identical secure keys. The fractional key rate can then be established by this expression in the asymptotic limit. It is taken to be simply as 1 minus the entropic measure of the QBER and minus the entropic value of QX. Now let's look at how we can experimentally implement the NBB84 protocol. In the lab, we prepare the 4-photon GHZ state using 2 photon pair sources shown in the blue shaded boxes. These are parametric downconversion sources using a periodically poled KTP crystal that's been embedded in a Sagnac loop to produce polarization entangled photon pairs. 1 photon from each of these sources then combines on a polarizing beam splitter, resulting in the desired 4-photon GHZ state at the output. Our users here are represented as measurement stages that can perform the Z and X measurements as required by the protocol. Finally, we note that the photon pairs that are created here are at 1550 nanometers, thus making them suitable for low loss transmission in standard telecom fiber. As such, we measured the noise parameters for the NBB84 protocol directly for up to 50 kilometers of fiber. And for the different lengths of fiber that we've considered here, we see that the fractional key rate remains largely unchanged. This shows a good level of robustness to noise for our GHZ states when sent over physical fiber channels. When looking at the overall conference key rate, we still see the exponential decrease as a result of loss in physical media, with just over 2 Hertz of secret key rates at the 50 kilometer mark. Nevertheless, this positively demonstrates the capabilities of creating a conference key when using GHZ states. In addition to these results, we also took a look at NBB84 protocol with finite key effects. So in practice, the protocol will only be run for a finite number of rounds, and as a result, the parameter estimation step will have statistical uncertainties which must be accounted for security. This leads to the following modified fractional key rate expression, which has been derived in this theory paper. In order to experimentally test this protocol with finite key effects, we implemented the measurement in round by round fashion and performed each of the steps in the NBB84 protocol for a range of different number of rounds, including applying error correction and privacy amplification to the raw keys in order to obtain these results. For this, we've observed very good agreement between the experimentally measured data points and the theoretically predicted line. For more details on the experiment, please check out our paper that was published in Science Advances just a few months ago. So our experimental work marks an important first step for demonstrating conference key agreement using GHZ states. The next step for us is to examine more broadly how this fits into future quantum networks that can support the connectivity of many users and hence may wish to use conference keys. It remains an ongoing task, but one may envisage a quantum network as seen here that consists of many nodes, some responsible for creating entanglement, even deterministically, while others are routing the resource states across fixed channels that form some overall network topology. Naturally, bottlenecks may arise, which would favor protocols that can operate efficiently, for example, minimizing the number of channel usages in the network. And this was precisely motivated by the original conference key paper, where the authors concluded that the NQKD approach can leverage the n-partite GHZ states to outperform the 2QKD case, where they must distribute bell pairs, as the use of n-partite GHZ states leads to fewer rounds to be performed over this constrained network where there are limited channels. Though this remained an open task for, in our previous work, begging the question how one might construct a suitable network primitive that can deliver the different entanglement resources required for each of these approaches in order to experimentally test this idea. So here we will consider the recently proposed network coding technique introduced in this paper, where graph states are defined for an underlying network topology for many nodes and can be used to distribute different entangled states to groups of the connected users. So specifically, we will examine this precisely in the context of conference key agreement. So let us now introduce the network primitive that we will be considering here. We have 6 users that will share a 6-photon graph as shown. The edge has a specific form of connectivity that is determined by these edges, which represent pairwise interaction that can between the connected nodes. What is special about this particular graph is that if we nominate 4 users, Alice, Bob1, Bob2, and Bob3, they are able to distill either the 4-qubit GHZ state or a set of 3 bell pairs in any combination among them, allowing them to perform conference key agreement in either the NQKD or 2QKD approach. To achieve this, we will be using a technique called local complementation that allows us to modify the connectivity of this 6-photon graph using only single qubit rotations, quantum measurements, and classical communication. This provides a modest expectation on capabilities of each of our users while placing the main resource-intensive requirements on the quantum network, which provides a reasonable basis for a network primitive. So now let's see how local complement techniques work. Starting from the resource state here, the goal is to arrive at this 4-qubit graph state between these users at the end. We remark that this state is locally equivalent to the GHZ state and therefore can be used for performing the NBB84 protocol as we demonstrated previously. So here the first step is local complementation, which gets us from the starting graph to this next one. The main thing to notice is the change in the graph, change in the edges of the graph. For a step-by-step mapping, we show this in the blue shaded region. In essence, we pick a target node here and isolate the neighboring nodes which share an edge with the target node. And then we toggle the edge relationships between the neighboring nodes. Note that this means that some of the times we will be adding edges while others we will be removing. In this case, we will add an edge between nodes 4 and 5. For a detailed look into how local complementation works in graph states, I would recommend this paper by Jeremy Adcock. Coming back to our task at hand, we need to apply another step of local complementation before performing quantum measurements on 2 of the nodes in order to remove them, finally arriving at the desired 4-qubit GHZ state. Now, putting all of this together, let us present conceptually our experiment for realizing quantum conference key agreement using the 6-photon graph state. The main point here again is that starting with this shared 6-photon graph, we can use local operations to obtain different entanglement resources for implementing different approaches to conference key agreement. We have already seen how we can obtain the 4-qubit GHZ state between Alice, Bob1, Bob2, and Bob3, which will enable us to perform the NQKD protocol. Directly below, we've outlined how we can go about distilling 3 bell pairs between Alice and Bob1, Bob2 and Bob3, and finally Alice and Bob3. We note that in this middle case here, we're able to distill 2 bell pairs at the same time, while the final bell pair needs to be distilled separately using this case shown here. So in the ideal case where we can prepare the 6-photon graph perfectly and perform all the local operations, including measurements, noiselessly, we would expect to see a performance advantage for the NQKD over the 2QKD approach, simply because the NQKD approach allows us to obtain a single conference bit using 1 copy of the starting 6-photon graph state. Whereas in the 2QKD regime, we will need a total of 2 copies of the starting state in order to obtain enough bell pairs. And so in the ideal setting, we would expect a performance advantage of NQKD over 2QKD of a factor of 2. Of course, in practice, there will be noise, and so we will be implementing each of these protocols and measure their respective noise terms. Then we can evaluate the performance in terms of the asymptotic key rate for generating the conference keys. Note for the 2QKD case, we first obtain the key rates for each of the bell pairs, and then we have to add these key rates together using this expression shown, which finally gives us the asymptotic key rate for the conference key when using 2QKD. So let's talk about how to prepare this 6-photon graph state. It is useful to first convert this graph representation to its equivalent circuit model form. Here we've denoted the 6 qubits labeled 1 through 6, and they are initialized in the plus state. Next, for each of the edges, we introduce a controlled Z gate, which acts between the qubits corresponding to the nodes of the graph. This now gives us the circuit form needed to produce the graph set that we have shown. We do note that CZ gates are notoriously difficult to implement in linear optics as they operate non-deterministically, and combining 6 of these together means that the probability of success is just impractically low. And hence we went off and optimized this circuit for linear optics demonstration using 3 key resources. First, offline entanglement in the form of Bell states that we can prepare directly from the sources. Next, linear optics fusion gates to provide the remaining interactions. Note that these are still probabilistic, but they perform at a much higher probability of success, and we only require 3 of these thanks to the use of offline entanglement. Lastly, we use local rotations or local unitaries in order to rotate the state and obtain the 6-photon state that's equivalent to the circuit that we've shown above. So now with the 6-photon graph state down, our remaining experimental technique that we will need to introduce is how we actually implement local complementation steps that are used to transform the graph. So let's take a look at the set of operations for the NQKD approach as an example. Just like the graph state, we can similarly map the local complementation step as a set of operations on the circuit model, specifically using local 1-qubit gates. Here we see that this first local complementation step, which acts on node 6, is realized by a set of 3 gates. Similarly, we can find the set of local operations corresponding to the next local complementation step. Then for the final step, we measure on qubits 3 and 4 to remove them from the graph in order to obtain the desired 4-qubit GHZ state for NQKD. In our experiment, we then measure the 4 remaining photons adhering to the NBB84 protocol, that is measuring the qubits jointly in X or Z in order to determine their noise terms and evaluate their asymptotic key rates. Putting all of this together, we now take a look at our experimental setup. For visual clarity, we've included a map here that roughly defines what each part of the setup is doing. Starting with our sources, we have a picosecond pulse laser to pump 3 parametric down conversion sources shown in the green shaded boxes. These use newly designed aperiodically poled KTP crystal that is phase matched to produce high quality photon pairs at 1550 nanometers without spectral filtering. For further details on the crystal design, we will refer to this paper. 2 of these sources are configured to produce Bell states directly, while the remaining one produces photons in the biseparable state that we initialize in plus states using linear plate polarizers. Next, in the main circuit, we use 3 linear optics fusion gates shown in the red shaded boxes. For polarization encoded photons, this simply corresponds to using polarizing beam splitters. And finally, for the Hadamard operations before the final fusion gates, we implement these using a half-wave plate. So finally, each of these photons will now go to each of the, to a measurement stage, which can perform arbitrary projective measurements in polarization using a quarter-wave plate, half-wave plate, and polarizing beam splitter, i.e. a standard polarization analyzer. Each of these measurement stages corresponds to one of the users in our network sharing the 6-photon graph as labeled. Here we make use of the fact that local complementation steps are composed of local operations that act on 1 qubit at a time, which can therefore be combined into a single unitary up at the end, and we apply this just before measurements. And along with the fact that we know what the measurement sequence are for each of the approaches, we can simply update the unitary measurements, unitary operations in order to perform either the NQKD or 2QKD protocols and measure their security parameters directly. So using the setup, we experimentally measured the asymptotic key rates for conference key agreement using the 2 approaches as shown in this plot. Here, the blue data points corresponds to the NQKD results, while the red data points corresponds to 2QKD. We looked at the fractional key rates here for each approach for a range of source brightness that is set by the pump power that we've used. We find that as the source brightness increases, that the key rate decreases, and this is due to added noise from the multi-photon terms that are produced in our sources. We should keep this in mind when we wish to compare the 2 approaches in terms of the actual conference key rate, where we see that the increase in raw 6-photon generation rate does outpace the drop-off in the fractional key rates, such that the optimal conference key rate is attained despite fairly modest actual fractional key rates. While overall our conference key rates shown here are certainly challenging, nevertheless, we observe a clear trend where the NQKD approach has outperformed the 2QKD approach when sharing the same 6-photon graph as the starting network resource state. To compare this quantitatively, we can calculate the ratios of the asymptotic key rates for each case. And we find that the NQKD protocol outperforms the 2QKD protocol approach by a factor larger than 2 in all cases. We do suspect that some of the larger values here are due to how the noise is distributed in the graph, which can lead to slightly worse performance for the 2QKD. This is something that we will wish to assess more carefully in the future. In addition, we performed one more measurement, this time at a fixed source brightness, and we measured over an extended period. We wanted to examine the long-term stability of our setup and see just how reliably the protocol can be run for long-term measurements. Here we show the results for each of the key rates for continuous measurement over 17 days. We note that no active stabilization nor re-optimization of the state preparation was performed during this time. We made sure to alternate each of the measurement types for NQKD and 2QKD over the course of this measurement to ensure that both approaches are similarly exposed to any systematic drift in the setup. Taking the whole data set together, we obtain a final ratio comparing the asymptotic key rates of the two approaches as before, obtaining a value of 2.13. So in summary, here we have experimentally demonstrated for the first time the use of a photonic graph state to implement conference key agreement in two canonical approaches, NQKD and 2QKD. Notably, both of these approaches can be implemented using the same starting 6-photon graph, which we use to represent our network primitive formed by 6 users. We picked 4 of these users who were then able to perform either NQKD or 2QKD by distilling the different resources through the use of local operations and quantum measurements. We then measured the noise terms for each of the cases in order to evaluate their asymptotic key rates. And we found that for the extended measurement that the performance of the NQKD over the 2QKD was just over 2. Moving forward, we would like to address the modest 6-photon rates that are observed here in order to explore other quantum communication and cryptographic tasks using this as a network primitive. Additionally, we want to examine the robustness to noise for creating and distributing this graph state over some appreciable lengths of fiber. And with that, I'd like to thank you for your attention.